Good day, good evening, everyone. Thank you for joining us today on this webinar. I hope everyone can hear me. We will just wait a few more minutes before we start when everyone is admitted, when everyone is able to see and to hear me. I will wait maybe for 1 or 2 minutes. And first of all, yes, thanks everyone for attending this webinar today. I'm very pleased that we have such a big number of attendees from all over the world. So everyone from all different time zones. For someone, it's maybe already late in the night. For someone, it's maybe early in the morning. And welcome, and I will try to make it exciting and interesting for everyone. So this is our technology webinar focused on continuous fiber 3D printing and the overview of the different technologies and different approaches to 3D print with continuous fibers to manufacture composite structures with 3D printing. So I think we can start. There is already a good audience here, I can see. Hello, everyone, once again. So I will start about a few words with a few words about who we are. We are a team of scientists and engineers who founded the Anisoprint company 5 years ago, and we are all of the founders. We are experts in composite materials and design and optimization of composite materials. And the biggest motivation for us to found this venture, to found this company, was to develop a new composite manufacturing technology that will not have all the limitations, which will be the most flexible composite manufacturing technology to allow to manufacture optimal designs with composite materials by the means of 3D printing. So what is actually composite 3D printing? To answer this question, we first need to answer what is composite. What is composite material? And by definition, composite material is artificial material that has two components, two separate components. And one of these components is namely the reinforcement, and the second component, at least two components, and the second one is reinforcement, and the second is matrix, which makes the similar reinforcing elements work together. And we want to 3D print this type of materials. So by definition, we can have different types of composite materials, which can have different types of reinforcing elements and different matrices. But it's very important to understand what is the difference between like composite 3D printing and a subdivision of it, which we call, or most of the experts call, continuous fiber 3D printing. That's not the same. So you can call a composite material something that is filled with particles or short or chopped fibers, which is also a composite by definition, but not by the actual physical meaning of it. So in contrary, you can have composite materials that are not filled with either particles or short fibers, but rather reinforced with endless or continuous fibers. And it is a big difference between these two. And only the continuous fibers, only reinforcing, gives us there is very high strength and stiffness, very high physical properties, and mostly because of the orientation of the fibers that we define with laying up continuous fibers in certain direction. With chopped fibers, or the material properties are not focused, they are not having a directional vector of the material properties, and they are basically the high properties of fibers themselves are basically dissolved in different spatial directions, and the properties are not that high. For comparison, like if it's a short fiber or chopped fiber filled polymer, then its strength can be probably as high as 100 megapascal, while with continuous fiber reinforced plastics you can go up to 2000. So that's 20 times or even more stronger material that you get with continuous fibers than you have with short fibers. Simple comparison, yeah, if you have something like a simple rod that you can 3D print with a chopped or short fiber filled plastic that can take you something like about 4 hours of printing, and such part will be capable of bearing a load of about, in this case, 16 kg. But if you put continuous fibers inside this rod, all along the rod, then the maximum load that it can handle will be more than 20 times higher than for just the short fiber filled material, with roughly the same weight, roughly the same printing time, but at of course at a high cost. But that's what you need to pay for the high performance. So to conclude this section, it's really important to differentiate between short fibers, between filled composites, and between continuous fibers, reinforced composite materials. That's completely different materials, resulting in completely different structures and properties. So we will be focusing only on continuous fiber 3D printing because that's the topic we work in, and that's what we believe is the biggest new emergent trend in 3D printing of the recent months, or maybe 1-2 years. And there are more and more players joining. There are more and more solutions becoming available in this field, and obviously it has numerous applications for functional parts, for manufacturing of functional and use load-bearing parts of very high strength and stiffness and very low weight. So why continuous fiber printing is so interesting, is so attractive for the market? Yes, as I mentioned, it's many times, about 30 times stronger than if you're printing with just plastic material. At the same time, it's 7 times lighter than steel, or 2 times stronger and 2 times lighter than aluminum. And there are wide applications in load-bearing parts such as tool jigs and fixtures, or custom spare parts, or functional prototyping. And in future, of course, we all believe that these materials and these technologies will be able to print functional end-use parts, but for that we need to ensure that these technologies and these materials are properly certified, and we know exactly how to design and what's the properties and what's the behavior of these materials under different conditions. Actually, there are different ways. It might sound quite simple. So there is a continuous fiber printing and there is short fiber printing, but there are many ways to print with continuous fibers as well. And just to name a few approaches for continuous fiber printing, on this page there are three of major ones. So one is called the Prepreg. So basically, as I said in the beginning, composite material is born when reinforcing material or fibers are mixed up with a matrix or polymer material, and at this moment, with a given ratio between fiber and matrix, with a given fiber and matrix material, the material itself is born. So the prepreg approach is when you preliminary impregnate, so that's where the prepreg comes from, where you preliminary mix fibers and matrix materials together, and then you get the material already, and then in the manufacturing process you shape it to a certain shape, you give it a shape, you give it a form. Another approach we call a co-extrusion. It's when you mix the reinforcing fibers with a liquid polymer material in situ when printing, when shaping, when manufacturing your parts. So the material is born exactly at the same time when it is being shaped to form a structure. And there is one more approach which is also interesting and can be used is with using commingled fibers or commingled fiber tows, when we not impregnate reinforcing fiber with the polymer, but we rather twist together high strength reinforcing fibers with polymer fibers that's in the process of printing are being melt and spread and impregnate inside the reinforcing fiber to bond the fibers together and to form a composite materials. So these are three different approaches that one can name when discussing the continuous fiber printing technologies. So first we will see what is inside the prepreg printing approach. As I said, prepreg is a preliminary impregnated material which can be either in form of a filament or in form of a tape, which already has a predefined or fixed continuous reinforcing fibers inside, and polymer matrix that bonds them together, and then in the printing process, which can look something similar to this. So it can be called a layup. So the prepreg is pushed or through the hot environment. So it's the polymer material inside the prepreg is melting, and then layer by layer it's deposited, it's extruded onto the part by the extruder movement, and layers of fibers or layers of tapes stick to each other, either under certain pressure or maybe just due to the plastic flow. There are well-known composite manufacturing approaches that exist for tens of years, such as automated fiber placement or automated tape laying, which use similar approach. So they also use prepregs. The prepregs can be either a thermoset or also thermoplastic, and they are heated up normally with a laser and consolidated with a roller and placed into a mold. So that's actually the big industrial technology, big industrial machinery for manufacturing of composite parts with fiber placement. And there are also new ways, new approaches to do that. So it's not anymore necessary to use a metal mold, but now you can 3D print a mold and lay up the tape or the fiber on top of the 3D printing mold. But in this case, of course, your consolidation pressure will be limited. But that's the way these technologies are developing also today. And Prepreg normally can give you a very good material quality, very high fiber volume fraction, which gives the best properties and low porosity and high strength and stiffness. But because of this pre-impregnation step, but that's not always enough. So what you also need is consolidation. So if you can make a very good prepreg material with a high quality material, but when you actually deposit it, when you extrude it, or when you lay it up, you need to have a good bonding between these prepreg fibers or tapes, either between layers or between separate fibers. So you need to apply pressure to push out the air that can be trapped between the layers, or to push out the pores that can occur. And this consolidation is actually a crucial step for the prepreg placement if one wants to have and if one wants to achieve good material qualities with a high fiber volume fraction. There are different ways for consolidation. So you can consolidate prepregs in situ with direct pressuring when depositing with a pressure roller or tools like that. But for that, you of course need a strong support. And if you are trying to put something like something like a thin wall or complex 3D structure, this roller, this pressure might ruin the structure. So it mostly limits the potential shapes that you can manufacture with a pressure roller to thin sheets. Another way to consolidate is in autoclave, which is under hydrostatic pressure, and at high temperatures the pores are being squeezed out from the material, but that's a second step. So the process will be now a multi-step. It will require dedicated machinery like autoclave to doing that, and still the pressures can be quite high, and complex 3D shapes might not be able to consolidate. Especially you can do the consolidation between the layers, but if you need to consolidate between the fibers, then it might be quite difficult to do in autoclave, because fiber will not allow the material to shrink. Another approach is overmolding, is when you 3D print or lay up something like a preform, and then this preform, you put it inside the injection mold or injection die, and then you inject extra plastic, or and by inducing pressure, the pressure that's induced by injection of the plastic can consolidate the material, can fill the pores to achieve good material quality. But for that, you need a mold, which also limits you in terms of the flexibility. And actually 3D printing, and that's what we believe in, is mostly about the flexibility in shapes and the flexibility in making changes. For overmolding, you will always need to manufacture a mold. And also extra plastic will decrease the overall fiber volume fraction. Why consolidation is actually needed? Here you can see the microscopic of a fiber placement of a cross section of a fiber placement technology of the materials that are manufactured with the fiber placement. So there is a lot of, still, if you are just using the pressure roller, there are still a lot of resin-rich zones and some porosity present in the, and you can clearly see the layered structure. And after certain extra treatment, only after certain extra treatment, you can get a good distribution and a good material property. Of course, one option, it's when you are laying up tapes, it's quite easy to consolidate them between layers by applying pressure, but what will be between two tapes? If you are placing tapes, there is a well-known problem of gaps that can happen between two adjacent tapes, or they can sometimes even overlap. And that's a well-known problem in the fiber placement because the tolerance is not ideal, is not so high, so you will always have these gaps and overlaps, and you cannot get rid of them with pressure consolidation. But if you are like placing fibers, not tapes, which are having a circular or maybe rectangular cross-section area, these gaps might be even more, might have even more significant influence. But the question is, how do you consolidate in this case, not in direction that is normal to the layer, but in the in plane directions? That's a big question. I do not know the answer, so that's probably a big problem with such approaches. Co-extrusion, that's the second approach, which where you simultaneously extrude through the same extrusion nozzle reinforcing fiber together with polymer material. So this gives you much more flexibility in terms of varying the fiber volume fraction or using different types of polymers as a matrix. So this approach is much more flexible than the Prepreg. But the problem is that if you do it with a thermoplastic, it's quite viscous, and it's normally very high pressures are needed to push the viscous thermoplastic inside the fiber tow, inside the dry fiber tow. So if you just do it simply as it is with the dry fiber and the thermoplastic, the impregnation quality will be very poor. You can clearly see this on a microscopy or even in an optical image. What can happen, what results you can get when printing with co-extrusion with fibers. So another approach is using this commingled yarn. So that's more similar to the Prepreg, but it can be more flexible in many ways. So when you have a yarn which you extrude through, again, this heated nozzle with reinforcing fibers, structural fibers, and plastic fibers mixed together. This is not actually a very common approach, which you find today, but it also works. So, of course, every technology has its pros and cons, and every technology would work better in different applications. So, with the prepregs, you can get very high material quality, very good material quality, very high material properties. However, you have to take care of the process, of the pre-impregnation process, to make sure that the material is actually a good one. So it's also a separate process that the material manufacturer has to establish to get good properties, to avoid porosities, to avoid resin-rich zones, and to get good distribution of reinforcing fibers. So, but the prepregs have many limitations. They have always the constant fiber to matrix volume ratio. With the prepregs, especially if it's a tape, you cannot have a curvilinear fiber paths. With prepreg fibers, you still can, but with tapes, you cannot. And the matrix material that is used is always predefined by the manufacturer, whatever he impregnates the fiber with at his prepreg manufacturing line. That will be only option for the matrix material. So on the pictures here on the right, you can actually see what type of fiber placement strategies you can have when using prepregs. So it can be either a solid infill or perimeters in case if it's a fiber prepreg. If it's a prepreg tape, then it's only straight lines where you can have where you can only have laminates with the straight fibers. With co-extrusion, you can have complex shapes. You can vary the fiber volume ratio, so that means that you can have layers of different thicknesses, or layers of varying thicknesses, or layers with a thickness drops or something like that, and you can actually make structures like lattices where fibers intersect, where you have ribs that have intersections and fibers intersect, and the fiber volume fraction in the intersection is doubled, but to maintain the integrity of the structure, the material volume still have to be constant. So actually the matrix volume in the junction, in the intersection, have to be reduced. So this is not possible with the prepreg because the fiber volume fraction is always constant, but it's possible with the co-extrusion because it's flexible. And with the co-extrusion on the customer side, it is possible, it should be possible to use different materials, different polymers as the matrix material, which also important in certain cases. Commingling is sort of a combination of both, but not actually, in my point of view, not in a good way. So the impregnation is better, is normally better, much better than in case of co-extrusion, but it's always worse than for the prepregs. And you still have the disadvantages that the fiber volume is constant and that the matrix material is fixed. The approach that is another way of combining both is what we call a composite fiber co-extrusion. How it works? You first pre-impregnate fiber with a polymer material to ensure good impregnation, high fiber volume content, good material quality. And then in the printing process, you use this material in a co-extrusion way. That's why it is called composite fiber co-extrusion. So it's actually not the co-extrusion with the dry fiber as we seen before, but with a composite fiber or a prepreg. But we intentionally do not call it a prepreg to differentiate between the prepreg placement technology, but we rather call it a composite fiber or reinforcing fiber. And we use it in the co-extrusion process. So the final material that is printable, that is printed with, we call a B matrix material. So it has reinforcing fiber, one matrix, which is actually a thermoset resin in case of an isoprint, inside the fiber toe, and another polymer, another matrix, which is a thermoplastic that is between the fiber toes. And so there are two interfaces. One interface is between the fiber and the resin, and the second interface is between the resin, the thermoset, and plastic, the thermoplastic. So there is no actual interface between fiber and thermoplastic. And it's quite easy to make, to achieve good impregnation, good adhesion between the thermoset and the fiber, and to achieve high fiber volume fraction in this material. So you can see it on a microscopy image, that the distribution of fibers is quite good, and the fiber content is very high, and there are virtually no porosity inside. So that's a very high quality material, and the adhesion between fibers and polymer is very good, because most of the reinforcing fibers have a special sizing for thermosets, and to achieve good adhesion of fiber to thermoplastic, you normally either need to remove this sizing or and apply some special sizing. But in this case, it's as simple as it is, and you get very high quality composite fiber, and then you get all the benefits of the co-extrusion together with the good material quality, such as possibility to print complex and curvilinear shapes that is not possible with the prepreg tapes, or such as using any plastic as a matrix material. So you can get materials with the properties that you need. Of course, strength and stiffness is the properties that are defined by the fiber, reinforcement, but there are other different properties, so like mostly surface or volumetric properties, such as temperature resistance or chemical resistance or resistance to wear or fatigue or impact resistance. So many other properties, or flame retardancy. So there is a big set of different properties that are governed by the matrix material, and with the co-extrusion you have the flexibility of choosing the one that is needed for your applications. And with a flexible fiber volume ratio, you can print lattices, which is a very big value for us as experts in composite materials, because we know that lattice structures and lattice designs bring the most optimal are the most optimal structures. So they bring the best of composite material properties into the structures, simply because that in lattices, every rib only works along the fiber, only works along the rib. So all the anisotropic properties of composite materials are fully realized. So the material locally always works along the fiber and not across. Printing lattices is only possible with a co-extrusion. How can you benefit from lattices? So that's the example, a simple example how one can benefit from lattices, from composite lattices in the 3D printing. Imagine you have just a plastic printed part, and of course it will have the highest strength if it is fully 100% solid, so 100% strength, 100% density. With a plastic infill, with a plastic cellular infill, you can reduce the weight, you can reduce the print time, you can reduce the material usage, but you will always lose in strength and properties. But with a composite infill, already with 30% of density, you get 350% of strength. So 35% of weight and 350% of strength compared to fully solid plastic material. So you save weight, you save material, you save printing time, and you get better, much higher properties. Actually, lattices are very well known in to be a real effective designs for composites. And what you see on the top is actually the composite lattice satellite body that is made with filament winding. The limitations of the filament winding is that the fiber paths always have to be geodesical and in most of the cases limited to shapes like cylinders. But with a 3D printing where you have much more flexibility in steering the fiber, in having the curvilinear fiber paths, you can manufacture complex shape lattices. Something similar to what you can see on the conceptual design of Airbus A2050, where the fuselage is seen as a lattice, which has a complex shape, curvilinear lattices, which obviously better to be made with composite materials. So that's the future, and that's the potential, what you can foresee and what you can get with the flexibility that only the co-extrusion approach to 3D printing with continuous fibers can offer. Thank you so much for your attention. I can now answer your questions, if any. I see that there is lots of messages in the chat, and maybe I'll start. If there are questions in the chat, I'll start answering them, and then we might go to a short Q&A session. So if anyone has a question, he might raise a hand, and then I can give permission to unmute the mic. We will see if it will work. But first, I will see if there are any questions in chat, and if anyone has also questions available, you can also post them to chat. Yeah, questions from Yannick, as usual. Hi, Yannick. This the person always asking very good questions. Question: in the co-extrusion process, how do you make sure of the impregnation consistency? Is there an online monitoring system recording this data? normally in the co-extrusion, in the printing process, in the process of co-extrusion itself, it's very hard to control or to monitor or to see the consistency or to get any data or any in situ data on the material properties, because that happens on the micro level. So to be actually able to see what's inside, you need a microscope, and that's not possible in situ. And as I said, if you are using the dry fiber in the co-extrusion, in many cases you will get poor properties that you will later see if you cut the sample, make the cross-section cut and look into the microscopy. So that's I would say it's not possible to do an online monitoring for the quality, but you can always do a microscopy afterwards. So if you are printing and using different materials and different settings, of course you can get different results. So that you should be able to afterwards check with a microscopy. Second question, if you print the same part several times, how good is the part-to-part consistency? I think that both questions that Yannick asked are referring specifically to our technology. So I can comment a little bit more than on the co-extrusion. In our case, we are not co-extruding with the dry fiber, so there is no need for the plastic in the co-extrusion to go inside the fiber. The fiber is already impregnated. So the material quality is much better than with the co-extruding the dry fiber. But again, you need to pick right parameters to make sure that the bonding between the fibers is good and there is no porosity between the fibers. So this can normally be done with microscopy. And part-to-part consistency, yeah, if you can maintain all the parameters, if you can control and maintain all the printing parameters quite well, such as printing speed and all the temperatures, extrusion temperature, chamber temperature, and many other settings, if you can control them precisely, then you get a very high part-to-part consistency. And this mostly depends on the components that you have in the system. So in our solutions, we have simple solutions like desktop systems, which are of course also have a good part-to-part consistency, but there is no live monitoring and live control of the system's parameters. So sometimes something might go wrong, and you might not be able to track everything. And to really get the industrial quality and industrial grade materials with a very good consistency, we have an industrial system with all industrial components where we can ensure the repeatability of all the parameters. I hope I've answered your questions. Next questions comes from Julian. In co-extrusion, how do you control manage temperatures for both the thermoset resin and the thermoplastic matrix? So we do not, both go through the same heat block. So both go through the same nozzle. The temperature, so there is a chamber where the composite fiber mixes together with a molten thermoplastic at a given temperature. So this is the only temperature we control. The temperature in the nozzle, in the print head. in our case, the thermoset in the fiber is already fully cured. The fiber is pre-impregnated with the thermoset, and the thermoset is fully cured. So what do we need to take care about the thermoset is that the thermoset at this temperature is above the glass transition, so it's in a rubbery state, so it becomes resilient, so that we can bend it at a certain curvatures, but the temperature is not high, is not very high, so that the thermoset will start degrading. But normally there is quite a wide temperature plateau where the thermoset is in a rubbery state and is quite stable. And the thermoplastic should be at its processing temperature and its extruding temperature, which might also vary in a certain range, or for different types of thermoplastics that can be different ranges. So roughly for a thermoset that we are using for the desktop systems, this range is from 150 to 300 degrees, and you can use you can process thermoplastics that fall, which processing temperature falls into this range. Another question from Smurti: how do you ensure proper bonding between thermoset resin and the thermoplastic resin matrix? This is a very good question. We use as a matrix, as a thermoset, we use epoxy-based material, and I would not say that it has good adhesion to every thermoplastic, but epoxies normally have very good adhesive properties. So it has good adhesion to most of the thermoplastics that you can have for the 3D printing. Of course, not all of them, and it's not always perfect, but with the tests that we have done, with the experience that we have, we rarely see the problems with adhesion between our thermoset formulation and thermoplastic matrix. And of course, there are some ways of surface treatment also that we use to improve the adhesion of the thermoset. So it's sort of specially designed and a special formulation to get good adhesion to a wide range of thermoplastics. How strong is the thermoset thermoplastic interface strength? It depends on many factors. It depends on the thermoplastic material, and it depends on the processing parameters that were used during printing, on the temperature, on the speed, on the layer thickness, on the cooling, and on many others. But in many cases, how do we assess? How do we evaluate this interface when we develop printing profiles, or when we do our material testing for different types of thermoplastic matrices? First, we look at it visually on the microscopy, and then we do the mechanical testing. So compression and tension and bending tests, and there by the failure mode you can see where actually the failure occurred, where the failure was initiated. And in most of the cases, we observe that the failure starts that the failure actually is inside the fiber tow, so in the thermoset, but not on the interface, or not in the thermoplastic. What is the surface of printed parts like? Smooth or rough? Very good question. So when you print with just the co-extrusion nozzle, so on all our machines, we have both on the desktop machines and on the industrial machine, we have both the CFC nozzles, the co-extrusion nozzles, and plastic FFF nozzles. When you are printing with just the CFC, with the fiber, the layer thickness can be quite high, so the surface can be quite rough. So on the composer, on the desktop systems, the layer thickness for co-extrusion is 340 micron, so it can be quite rough, and the surface is not smooth. But with the second nozzle, with the FFF plastic nozzle, we can encapsulate the composite inside the plastic shell, and this is done automatically in the software. So you define, and you can define much better thickness tolerance for the plastic shell. For example, this is what we call a macro layer approach. So when you have the macro layer, which is a fiber layer, which is 340 micron, and then you have two plastic shell layers of 170, or like 3 or 4, to get a much thinner layer, to get much better surface. And also by using certain types of plastics for this external shell, you can get very smooth surface. Like, for example, if you are using chopped fiber filled plastic grades, they normally give very smooth, very nice made surface finish, and that's what you can get also on our machines by using such materials as an external shell material. Question, any difference between polymers? I'm not sure if I understand the question correctly. Yeah, but I will try to answer still. If you are using different plastics, either on the co-extrusion or on the plastic shell, areas, yeah, you can use different polymers for that. And these polymers, if it's on the surface, then the surface properties will be affected by the will be defined by the polymer that you are using. So if you need certain resistance to certain chemicals, you might use polymers that are resistant to whatever is in certain acids or certain oils or something like that, and get your part protected, you know, from these environments. Or you can use soft polymers or rubber-like to get something that is stiff in direction of fibers and soft in the other directions. Or so that's gives you this freedom, and you can use different polymers to get different results. If the fiber gaps and lapse issue similar to AFP. In the co-extrusion, normally we do not have the fiber gaps problems, because the plastic flows. It's not trapped inside the fiber, so it can flow, and the fiber volume fraction is lower, so you do not need consolidation. So basically, we make sure that there is enough plastic that without consolidation, plastic can flow into the zones between the fibers to make sure that there are no gaps. How much time does it take to create an FEA model of the print design to simulate it first? It depends on the complexity. It depends on many factors. Of course, it's not such an easy job, and we are also working on the solution to make it easier. So there will be a special software that we will offer to actually that will automatically create an FA model from a G-code, from a sliced model in Aura, so that you can later open it in one of the commercial FA simulation software and do the simulation. But that has to be done then in iterations. So you first slice, you have certain reinforcement scheme, then this software will do the mesh automatically and identify all the material properties and the material directions and every element, and then you can do the simulation. But now we can also help you, because that's certain knowledge needed if you want to create an FA model with all the anisotropic material properties and what finite elements can be used for that and what are the properties of the materials that needs to be put. So if you are interested, please contact us and we can help you with trying to do the FA simulations. In the process of combining dry fiber and resin, how does your process reduces porosity? Can it be improved more? The process of combining the dry fiber and the resin is actually quite simple, and it ensures, so with the impregnation we can make fibers with like close to zero porosity. So there is actually not so much to improve, but what can happen, you can get extra porosity in the co-extrusion process itself, and this depends very much on the process parameters. So what is the temperature, what is the print speed, what is the layer thickness, and many others, so in this process you can get some new pores emerging. So that's this is where the improvement might be necessary in identifying right parameters for co-extrusion to get a real high quality end material. Is there a maximum temperature which the resin system of the anisoprene filament can withstand? Does the limit the melting temperature of the thermoplastic matrix? Yeah, on the desktop systems, on the composers, the limit is 300 C. With a high temperature, the thermoset inside the filament will start degrading, and so that's why there is this limit. Also on the hardware, and you cannot go higher than that. But on the Prom IS 500 machine, it's a high temperature machine. So there we are offering special fibers, high temperature fibers that can be processed with high temperature polymers such as PEEK, PEKK, or PEI, or other engineering high temperature materials. Have you looked at using pultruded thermoplastic profiles versus the thermoset? I think you might achieve a similar benefit with more toughness and better bonding. Of course, that's a very good comment. And yes, we are also looking into that. It has certain benefits versus thermosets, you're right. It has certain drawbacks as well. But yes, we also have such materials in our R&D being tested, and maybe we will also offer it, especially for the high temperature solution. And we are also looking to find good partners in this topic. So if anyone can offer something, we are open to discussion. Please write us. Please write me directly, or please write us to info@anisoprint.com, and we can probably find some good basis for collaboration. Thanks, Yannick, for good questions as usual. Thank you. Next question: when a part is tested to failure in the mold shear, always with the within the thermoplastic domain. When we test samples in bending, it's still, in many cases, it's the fiber failure. So if it's a pure shear, we actually never did the pure shear test, so the interlaminar shear. If you would do such test, I assume that it might, I'm not sure, it will actually depend on the thermoplastic itself, and on many other cases where actually the failure will happen. So it's a good question, but I have no good answer. How to compare the anisoprint CCF with Markforged forced fiber 3D printing? It's simple. So Markforged is a Prepreg based. So Markforged pre-impregnate dry fibers, either carbon, Kevlar, or glass, with nylon, with a fiber volume fraction of about 28%, and then that's just simple material deposition where they melt the plastic inside the fiber tow and then they place it. And we have co-extrusion, so the fiber and plastic is mixed during the printing. So and this gives these benefits which I've mentioned actually during the presentation. So flexibility in fiber volume ratios, capability of printing lattices, and capability of using different plastics as matrix. Generally, there is a fiber jamming problem in processes like continuous fiber 3D printing equipment. How do you ensure not jam fibers? Yes, that is a problem, and that can happen. What in our system, how do we ensure that it's not happening? First of all, that's the fine-tuned process parameters. So if the process parameters are not very well tuned, so like there is an over extrusion of plastic or something like that, you might get jamming. Second, the zone where the fiber mixes with the plastic is actually a very thin layer at the very output of the nozzle. So it happens almost at the nozzle tip, where the plastic covers the composite fiber, so there is no so much space for the fiber to buckle or to jam inside. So the mixture happens almost at the nozzle tip. Then the fiber is stiff. That's why we call it a composite fiber. It's fully impregnated, fully cured, so it's very stiff. And when we pull it through this thin plastic zone, it still remains stiff. So there are different tricks and different ways how do we make sure that jamming does not occur. But with good profiles, good process parameters, it actually never happens. But if you are playing around with the parameters, there is a chance of jamming, and you are right, that can be a problem. What are your thoughts on in situ dry fiber impregnation with UV? Yes, I didn't mention this approach in this presentation, but yes, it did exist. So the co-extrusion with dry fiber and UV curable resins. UV curables thermosets in uncured state normally can be not very viscous, and they can impregnate fibers very good. So the dry fiber co-extrusion could work quite well for the UV curing, and we know such technologies, for example, like MOI or continuous composites, who do that, and that's actually quite good technologies. But what I see as a drawbacks, first, the UV curables normally not so high performance resins, especially in the temperature properties. So there is this drawback. You cannot really make a high temperature material with UV curables. And also in the process, you need to make sure that the UV light goes all through the fiber inside. So it's not so simple to do it with carbon, which is non-transparent. But yeah, this technology exists, and with the only big limitation that I see is the temperature of the final part of the temperature properties. Is there only one hot end for plastic and carbon? Yeah. On the desktop systems, on composers, we have one hot end for plastic, one hot end for CFC. So actually there are three inputs, one input for the plastic nozzle and two inputs for the CFC nozzle, one input for fiber and one for plastic. So there are three inputs, two plastic and one fiber, and two nozzles, two hot ends, one FFF and one CFC, and they are switching. So the plastic nozzle is tilting there and back, and the machine switches between them. It first prints with plastic, then it prints with composites, and it changes between layers and between different zones. So that's how it works on the composer. On the PromIS, there is a tool changer for 4 print heads, where you can choose which type of print heads, which type of hot ends you want to use. You can use all 4 of them plastic, or all 4 of them CFC, or combine in a certain way. Thanks for your questions. Is your machine suitable for only certain type of thermoset resin and thermoplastic? Can I know the cost of CFC 3D printer? Our machines are so it's an open system for the thermoplastic. So you can use any thermoplastic that is available on the market in the form of a filament to print on our machines. So it's open. And for the fiber, it is on the desktop systems, there is a certain type of thermoset that we use for the impregnation, and the composite fiber has to be sourced from us, and that's the only way how we can guarantee that the system is actually working. However, you can also use different other fibers that we do not provide, but in this case we cannot guarantee any result, we cannot provide warranty, and we cannot guarantee the quality. But the software with all its settings will allow you to find the right combinations of parameters to be able to work with also not the fibers that we provide. The desktop machines, we have 2 sizes, the A4, which has the build area of an A4 paper size, and A3, which is twice bigger. And I can only name you the list prices, the manufacturer recommended sales price in Europe, in euros, but for more exact price, you will need to contact your country, you will need to contact one of our distributors in your region, in your country. So the list prices in Europe for A4 is 12,000 euro, and for A3 is 24,000 euro. Your machine is suitable for high performance thermoplastics, or which ones are suitable? So the Composer, the desktop machines are not suitable for high temperature thermoplastics. So the most high performance and the most high temperature material you can probably use on the Composer are certain PA grades or PC polycarbonates. That's the maximum you can have on the desktop machines. But if you need a high temperature, then there is a ChromeIS machine that can print with high temperature plastics up to 400 degrees C and higher. Is there any pre-processing or post-processing required? Post-processing, normally not, but it depends on what type of surface do you need. So if you need a paint finish, then of course you need to post-process it, as most of the normal FFF printed parts, and there are different solutions for post-processing the FDM, because you will still have this layered structure. It can be also quite with a quite nice finish if you use certain types of plastics and certain layer thickness, so it also has a beautiful aesthetics. So you might not need any surface finish, even if it's an aesthetic part. But if you need a paint, then you need a finish. And pre-processing, no, there is no pre-processing needed. Which porosity percentage the process can achieve? That's a good question. So we can achieve in a certain regimes, we can achieve the porosity of less than 2% without any post consolidation and post treatment, but that's not something that we can today guarantee for every part or every structure that is printed, because especially on the complex shapes, on the curvatures, it might change, or it really depends on the processing parameters. But there is certain procedures that needs to be done, which you need to follow if you need a real low porosity, and with certain plastics and certain regimes, you can have less than 2, and if it's really important, yeah, then it will require some tests, but it's achievable. How do you deal with the big temperature gradient for the 300 degrees C materials? So the temperature gradient, which type of problems can it cause? First of all, I think that what problems you can have is the warpage and the interlayer bonding. So on the 300 degrees C, it's actually not so critical. And for the warpage, if you are printing with continuous fibers really help to prevent part from warpage, so it helps. But on a high temperature, yes, indeed, there are problems. So that's why on a high temperature machine, we have a heated chamber to print with high temperature material. In many cases, you will need a heated environment. So that's why on ChromeIS, there is a heated chamber where you heat the whole print zone, and so the gradient is not so high. So this helps to solve these problems. What do you suggest for non-destructive inspections of parts made by this process? Well, as usual for composites, you can use ultrasonic to track large porosity, if any. Normally with ultrasonic, you will not be able to see individual fibers. You should be able to see fiber bundles and large porosity. But yeah, I think that ultrasonic can give good high-level results to assess the porosity. But of course, X-ray micro-CT is always better, so that on some systems where you can even go to individual filaments and being able to find internal porosities, but then you are limited maybe to certain sizes. Generally, most of the standard methods that work for traditional composites will also work for 3D printed. Can we use the cutting code for abacus simulation calculation? I'm not sure what is cutting code. If you mean that it's the G code that we generate in Aura, or so the fiber paths that we have in Aura, that's the tool that we are working on, but it's not yet ready for release. So far, you will have to have a separate model for that. But if I didn't understand your question correctly, can you please clarify, and I will try to give you a better answer. Are your fibers interchangeable with Markforged fibers? Is your fiber technology open for third-party suppliers? We have some customers that did print with Markforged fibers, but that's much more difficult than printing with our fibers, because Markforged fibers, they will, of course, tend to buckle much more, and they have much lower fiber volume fraction. So when using Markforged fibers in our systems, you will get, because you will need to add extra plastic as well, and then the fiber volume fraction will be much lower, because in the Markforged fiber itself, they have 28%, and when you add another 30, 40, 50% of plastic during the co-extrusion, then the fiber volume fraction will be very low, and there is much more chance that it will be jammed because it will become soft much faster in the chamber, because there's a thermoplastic that will start flowing and start melting at much lower temperatures than our thermoset fiber does. But playing around with materials and playing around with the settings, you can do it. You can even print with the dry fibers, but that's even much more tricky, because then you cannot actively feed, you cannot cut and restart, so that's obviously only for research purposes, and you really need to know what you are doing. Within your existing base of users, do you have any feedback on whether your machine are mostly used for making tools, jigs, prototypes, or the final actual use parts? I would say that within our existing base, there are three main customer segments by application. That's indeed tools, jigs, and fixtures, which is the biggest one. The second one is functional prototyping. So customers that are developing new products, they are not yet into the serial production of the new products, but they need to get certain first batches quickly and functionally before they really go to a large-scale production. And this is where it's effectively applied because of much shorter production cycles and much shorter manufacturing preparation costs. So that's also the big one, and the spare parts, some custom spare parts. So final parts is not so many in a true meaning, because of mostly the certification and things like that. But that's what the ChromIS machine will be really focused on, and that's where it's intended to. So, and we already have first customers that will receive the first Chrome machines early next year with the end use up, and most of them have the end use applications. So, and the Chrome machine is really designed for production run, for 24/7 run, so it's reliable with all the industrial requirements and all the industrial components. So on the Prom, we expect much bigger number of customers using it for final actual end-use parts. What kind of fiber placement strategies do we offer? How to design easily the shown on the slides, fiber structure, and adapt it to the shape of my part. So what do you have here? So you first design a 3D model, and then you open this 3D model in Aura software. And in Aura, you can have different fiber placement strategies, which are namely the reinforced perimeters. So in every layer, you can define any number of fiber perimeters or fiber infill. Fiber infill is what's left when you subtract the perimeters. So, and we have 4 types of infills available, 4 types of fiber infills available. One is a solid, where you like lay fibers layer by layer, maybe giving different directions one next to each other to actually make a laminate, or lattices. We have 3 different types of lattices for which you can define the density, the type of the lattice, the density, and the directions of the lattice ribs for the actual part loading conditions. Can you print 2 parts at the same time? Yes, you can, but this will not give you too much time savings, because this material will be extruded for one part and then on another part for every layer, so they will grow simultaneously, but it will be actually the same, almost the same print time if you print one after another. What can help you to save time, if you like, if the part is like really 1-2 hours print, and you want to live and you want to print several parts overnight, then it might make sense to have several parts printed at the same time on one table. Can we use the printer's fiber path planning model into simulation software for calculation? Not at the moment, but very soon we will offer that capability. There is some control for storage or some raw material preparation before printing. Yes, that's a very good question, because most of the plastics require certain storage conditions. Most of the plastics need to be dried. If the plastic absorbs a lot of moisture, then the printing quality will be bad. So, but that's depend on what plastic manufacturer recommend for storage of the plastic material. For fiber that we provide, there are no special requirements. So you can store it and use it as you find it comfortable. With 2 hot ends, no. On the composer, there is one print head with 2 hot ends in a fixed position. So only one is active at the moment, and so you can print only one. Only one hot end is used at the moment, so you cannot print with 2 hot ends on either on the composer and on Prom as well. Thanks everyone. That's already hour and a half. Thanks for questions. That was so. Then we are finishing with a very good timing. And thanks everyone. And have a good rest of the day. And thanks for attending.